In this video, what I'm going to be talking about, I'm going to be talking about VSEPR, valence shell electron pair repulsion. Or another way is we're trying to come up with the molecular and electron geometries, the domains. What is the shape? When I say VSEPR, what is going to be the shape of these? In order to do this, we want to come up with a Lewis dot structure for these. And so for the first example, what we've got is we've got hydrogen cyanide. Carbon is going to be the central atom. It's going to be triple bonded to a nitrogen. And then it's going to be singly bonded to a hydrogen. Now, the molecular geometry means that we're just looking at, you want to focus on the central atom for this. You always want to focus on the central atom. And so if we look at our central atom, it's going to have basically two domains. Here's a domain, there's a domain, and it doesn't have any lone pairs on the central atom. And so this becomes linear. As well as the electron domain is going to be linear. If there aren't any lone pairs of electrons on the central atom, the molecular geometry and the electron geometry are going to be one and the same. The electron geometry means it's going to account for any lone pairs of electrons that happen to be on the central atom. If it's the molecular geometry or the molecular domain, you don't worry about the electrons on the central atom. And as I mentioned before, if there aren't any lone pairs of electrons on the central atom, the molecular geometry and the electron geometry are going to be one and the same. Here we have the sulfurous anion. Once again, we're going to count the valence electrons so we get the correct Lewis dot structure. You got to get the correct Lewis dot structure. If you don't, you can't do this. So sulfur has 6, plus each oxygen has 6, plus now we have 2 extra electrons here. And this is going to give us, this is a 4 times 6 is going to be 24, plus 2 more is going to be 26 electrons. All right, so we have to come up with 26 electrons for space. I'm going to erase this. We know that we have to come up with 26 valence electrons for this one. And sulfur is going to be our central atom. And we're going to have a double bond here for an oxygen. And the remaining oxygen atoms are going to be singly bonded to the sulfur. All right, so our -1 charge, -1 charge. And then there'll be a lone pair of electrons here because we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now there becomes the 26th one. Now, you'll look at the central atom, and the central atom has 4 electron domains. 1, 2, 3, and 4. Since it has 4 electron domains, the electron geometry of this is going to be tetrahedral. And because the sulfur has this huge lone pair of electrons, which is going to take up a tremendous amount of space, is going to force the oxygen out of plane, this becomes trigonal pyramidal. If it didn't have that lone pair of electrons, it'd be trigonal planar. But because it has this massive lone pair of electrons, that's going to repel valence shell electron pair repulsion, VSEPR. It's going to push these oxygens out of plane. Here we have sulfur, oh my goodness, I just forgot, SF4. And so we want to count the number of valence electrons, so sulfur is going to have 6, plus each fluoride is going to have 7. And the number of valence electrons for this is going to be 34 electrons. All right. Now, sulfur is going to be our central atom. We have 34 valence electrons we have to account for. Oops, I'm going to erase this so we have some room up here as well. I don't want to run out of board space and you not be able to see it. That's sulfur tetrafluoride. Sorry, I kept thinking what 4 is. It's sulfur tetrafluoride. And so we have sulfur And we're going to have a fluoride here, a fluoride here, a fluoride here, and a fluoride here. We start putting valence electrons around this. As such. Now we're supposed to come up with 34 valence electrons, so we have 4, 4, 4, 4, that's 32, so there's going to be another pair onto the sulfur. Now, because you count the number, you look at the number of domains around the sulfur, you have 1, 2, 3, 4 for the fluorides, and then you have this lone pair of the sulfur, that's going to be 5. So there's 5 domains around this sulfur, and this is going to be then trigonal bipyramidal. Is the electron domain, because you have to take into account that lone pair of electrons. Because of that, what this is going to cause the molecular geometry to be is that this becomes what is called a seesaw. So it sort of looks like a seesaw is the shape of it. We have a few more examples here. All right, so we have phosphorus hexafluoride anion. We've already seen this one before, so I'm not going to spend a whole lot of time, or I'll go back through it again. So we have 5 valence electrons plus 6 times 7 for each fluoride plus 1 gives us 48 electrons. And that isn't showing up that great. I'm going to go back to this one. And this molecule will be as such. All right, so it'll be as such. Now, this is going to be octahedral. And because there are no lone pairs of electrons onto the phosphorus, the molecular is going to be octahedral as well too. Oops. Will be octahedral as well too. Now, if we can look at ammonium chloride anion, the ammonium chloride anion, oops, that's I already made a mistake. That's supposed to be plus, that's not negative. We count the number of valence electrons. Each nitrogen has 5, plus 3 of the hydrogen, plus 7 from the chlorine. Now, this plus means that we are losing an electron. The plus means we lose an electron. And this tells us that we have now 14 electrons. And so we draw the nitrogen as being the central one, and then this is going to have a hydrogen, a hydrogen, a hydrogen, and then this becomes a chloride. We put the lone pair of electrons around the chloride. Now we can start counting the number of valence electrons. So we have 2, 4, 6, 8, 10, 12, 14. We now have 14 valence electrons. We have 4 things bonded around the nitrogen, so it's 1, 2, 3, 4. So this becomes tetrahedral. Because there aren't any lone pairs onto the nitrogen, that is tetrahedral as well. That becomes tetrahedral as well. Now, we have N3 minus. This is what's called azide. This can be somewhat of a difficult molecule to work with a little bit, coming with the Lewis dot structure. But let's just first calculate now the number of valence electrons. So we have 3 nitrogens. Each nitrogen has 5 valence electrons plus 1, which gives us 16 electrons. Gives us 16 electrons. I'm going to erase this guy right here so we have a little bit more room, because there's a couple structures we can draw with the azide anion. So one we can draw is we can have nitrogen double bonded to nitrogens everywhere as such, and then there's going to be two electrons here, two there, two pairs, I should say. Now if we start counting the number of valence electrons, we have 2, 4, 6, 8, 10, 12, 14, 16. Must have counted 16. Yeah, 16, that's right. 2, 4, 6, 8, 12, 14, 16. 16, that's right. Now if we're going to calculate the formal charge of these, we find out that the formal charge of this becomes +1, this becomes -1, and that becomes -1. So that's one Lewis dot structure we can come up with the azide. That's one. Another one we can come up with, I want to show you why the formal charge is so important. Another one we can come up with is we can actually put a triple bond between two of the nitrogens and a single bond here. So if we're going to put a single bond there and then a triple bond here, now we start counting up the number of electrons, 2, 4, 6, 8, 10, 12, 14, 16. This will have a formal charge of 0. This will have a formal charge of +1, and this will have a formal charge of -1. Now the more correct structure for this is that one right there, because now only 2 of the atoms are charged. All right, but that doesn't have any difference in the electron and molecular geometry. I just wanted to show you how the formal charge is important for determining Lewis dot structures. Now we look at this nitrogen. It has one domain, two domains, so it only has two domains, and there's no lone pairs of electrons in the central atom. So this becomes linear, and the molecular is linear as well too. All right. So once again, if you're going to be coming up with the geometry of these molecules, it's important that you are able to do the Lewis dot structure. And if you have any questions on Lewis dot structures or on these molecular geometries, feel free to ask me questions.